Right, let's work on another problem. Today we're going to be working on lowest common ancestor of a binary tree. This is going to be the first problem of the day. So, LeetCode number 236, lowest common ancestor of a binary tree. Given a binary tree, find the lowest common ancestor of two given nodes in the tree. According to the definition on Wikipedia, lowest common ancestor defined between that has both P and Q as descendants, and we allow a node to be a descendant of itself. Interesting. So, let's see. What we could do is, I think that this, like many other, I guess, sort of recursive problems or binary tree problems, probably falls within some degree of recursion. So that's what I'm thinking first of all. The other thing is that we could probably take some cues from what we did with another LeetCode easy. And that was a similar problem, but lowest common ancestor of a binary search tree. I forgot exactly which LeetCode number that is, but I do recall that it's a LeetCode easy. In that one, we said if a number is between P and Q, then it is the lowest common ancestor. If a number is greater than both, then it is not, I believe this is also inclusive. If it is greater than both, then an LCA exists which is less than the current number or the node. Similarly, if less, then LCA exists which is greater. So this is sort of the idea or the pattern that I recall from lowest common ancestor of a binary search tree. Now, what are the problems that exist in this case without a natural order invariant? And what I mean by a natural order invariant is that the binary search tree has an invariant which says that the left subtree must have values which are less than the current node, and the right subtree must have values which are greater than the current node. That's the invariant of the binary search tree. Now, what happens when we don't have this binary search tree invariant, and we only have a binary tree? No searching. The first thing is that we don't know where P and Q are. Now, within the context of this problem, we are given that P will exist within the tree. It's a little hidden by my webcam, but it is a constraint of the problem. So at least that's one part that we can consider, right? They do exist within the tree, so we must have a solution. But we don't know exactly where they are. They could both be in the left or right subtrees from a given node, or they could be split up, right? One could be in the left subtree, one could be in the right subtree, or they could be both. They could be both in the left subtree or both in the right subtree. We don't quite know. So that's the main problem, right? Because if we don't know where they are, then we can't really tell exactly which direction we should go. Because, well, we don't know where they exactly are. If they're both in the left subtree, then we should probably go to the left subtree. and check there to see if there's a lower common ancestor than the one that we have currently. However, if they are both on the right subtree, then we should go to the right subtree, the root at the right subtree, and we should check there for a lower common ancestor. And if one is in the left and one is in the right, then I think that we can assume that in that case, that we are currently at the lowest common ancestor. So in this case, I think the most naive solution, or I guess I wouldn't say naive, but at least the brute force solution, is that we will run a traversal across the left subtree and the right subtree to produce a set of both sides. Right? So we'll produce a set on both trees, on both subtrees. We'll produce a set and then compare to see if both are on the left, both are on the right, or one exists per side. And then we can say that if both are on the left or both are on the right, then we can update our root / least common or lowest common ancestor to that root and continue on. And in this case, if we do a traversal, we would have to be a little bit careful to, I guess, make sure that we don't accidentally traverse through the entire tree. We only want to really traverse over the left and right subtrees, right? So that's the naive solution. Well, what would this cost? Well, the first iteration at the root would cost O of n over 2 for the left plus O of n over 2 for the right, which is just O of n linear time, where n is the number of nodes in the tree. So we take one half, we take another half. We assume that we can assume that both of the sides are balanced in this case, though it doesn't really matter. If one side has n over like 10 and the other has like 9n over 10, it really doesn't matter, because ultimately we care about the asymptotic notation. Well, in the second iteration, assuming that we go on one side of the tree, we would have O of n over 4 plus O of n over 4, which is again O of n asymptotic, and so on and so forth. We would go down, so a half, or we would have O of n plus O of n over 2 technically, right? If we're talking about like precise measurements. So take 1, then a half, then a quarter, then an eighth, a 16th, and so on and so forth, until we reach the leaves, or until we find the LCA. So this is a sort of the start solution that I'm thinking about. This asymptotic notation of having 1 plus a half plus a fourth plus a 16th, amortized, that would be constant time maybe. And the reason why I say amortized, it sounds like constant time, is because this seems very close to something that I've seen before, which is sort of the argument for the constant time insert at the end for a dynamic list, or a dynamic array rather, where every time you hit the capacity of the dynamic array, you double the array, and you copy the items over. If you are starting from the initial amount, your first couple of operations would force a double pretty quickly. If you're starting from empty array and you add 1, well, you have to double it there. Add another element and you have to double it to 2. Another element, the third one you don't, the fourth one you do. And so on and so forth, right? And that sort of pattern continues. But if you spread it out across all the way until n, well, you take 1 and then a half and then a quarter and so on and so forth, but amortized, that's constant. So I think there's an argument to be made here that potentially that this could be constant time amortized. But I think it's more genuine to say that this is probably very, very close to a linear runtime scenario. So I'm going to say amortized. An argument could be made for O of 1, but realistically, probably linear time. And I think that this is a pretty okay solution. And with that, I would probably start coding here. So let's get started actually coding up this solution. Of course, we should also, before we start coding, think about the space constraint of our problem. And in this case, our space constraint would be interesting because we would first start off by holding about the entire array, all the nodes in the list. Then we get about half, then a fourth, and so on and so forth. And once again, we hit a situation where we probably will, at least at the most, we are bounded by the fact that at the beginning we have to store our entire list of nodes, at least within the traversal, right? So I'm going to say that the space or the memory will probably be around O of n as well. But with that, let's actually start coding. So we can say left set is equal to mutable set of tree node. And we can say right set is also mutable set of tree nodes. We know that we are given that all the node values are unique, so we could actually just do an integer set to save a little bit of space, I suppose, right? Though we could also hash into the node arrays, or the node references themselves. That's also possible. So now we can get started. So we can say, let's see. Well, let's check out our constraints as well. Is a root guaranteed to exist? Well, yes, the number of nodes within the tree is in the range of 2 to 10 to the 5 inclusive. That means that there will always be a root, and the minimum that we can have is that the root either has a left or a right, in which case the lowest common ancestor will be the root. But we don't quite know that yet. So let's create a secondary function called build set. This will be rooted at some node, and we'll have this node be non-null. And then we'll have a mutable set of integers, and we'll call this set. Looks like that's a reserved word. So we'll say, what could we call it? We'll call it node set, and this returns nothing, right? Because we're just building on this node set. And we can run our traversal as usual. So what we will do is that we'll run our standard pre-order and post-order traversals, or in-order traversals, we'll say. So we can say that if root.left, then we can say build set at root.left, and we can just pass in our node set. Then we can say node set add, and we'll add our current root. And if root.right, then build set root.right node set. So this is a fairly simple in-order traversal. We explore our left, we explore our current node, and then we explore our right. Since we're passing in this node set by reference, we don't need to return anything special here. So we can say left set, let's see, we can say build set, we can say root, and we can say if root is equal to null, return null. This way, now when we reference root later on in our function, we know that root is not null, and hopefully the compiler is smart enough to realize that. So we pass in our root with our build set, and then we'll pass in our left set. We'll pass in our root for our right set, and actually we need to push a left and a right. And we'll say if root is null, we can just return. And that means that this is potentially nullable, right? And this is mainly because we're not sure if a left or right exists for our root. Then we can say when left set contains P and right set contains Q, and we need to grab their values. And we can say if P is null or Q is null, we can return null as well, just so we don't have to address that there, hopefully. So now if either of these are in the case where one of them exists within a set, within each set, so left set contains q.val and right set contains p.val, we can return our current root. However, if left set contains p.val and our left set also contains q.val, then we want to probably return our lowest common ancestor centered at root.left, and we can pass in our p and q. Otherwise, we can just return our lowest common ancestor called on the right side, because that's the only other situation. So that sort of covers everything, all the cases that we have in that case. So once again, this is our sort of bare bones like draft solution. So we create a set for the left and we create a set for the right. These sets indicate sort of these sets indicate what elements exist within our left and our right subtrees. If one exists in one and if one exists in one and the other exists in another set, then we know for sure that that our current root is the lowest common ancestor. If not, then we recurse on whichever side has both of them. We also need to think about the case where one of the nodes, P or Q, is actually the root. In that case, one of the sets might be empty or might not contain the element, and the other set will contain the element which is not the root. We should also handle that case. I'm not quite sure if this algorithm that we've created so far actually does handle that case, so let's handle it explicitly. So we'll say that if root is equal to p, and this will be in A here. Left set contains p.val, or sorry, q.val, or our right set contains q.val. Then we return p. If our root is q and our left set contains p.val, or our right set contains p.val, then we can return q. So this is the case where our root is one of the elements, p or q. And in that case, we don't really care that they exist. One of them exists in one and the other exists in the other, because one of them is a root. So this is also another case that we would want to handle. This is one of the more, I guess you could call them edge cases or corner cases, where one of the roots, or one of the values that we want, p or q, is actually the root, is actually the lowest common ancestor of the other root, or the other node. So that should be most of the edge cases handled. Perhaps there are a few that I have overlooked. But I think that with this, let's just take a double check. So if root is null, return null. If p or q are null, then we return null. This should allow us to reference root, p, and q underneath in this area without doing a null check. We create our left and right sets, and then we populate them using this build set function that we've created. This build set function is pretty straightforward. If our root is null, then we just return. Otherwise, we do an in-order traversal, so starting at the left, and we build up from there. And then we add our root after we've explored all the way to the left, and then we explore the right. In-order traversal, pretty straightforward. Then, once we have those two sets, we can evaluate them. So if it contains p on one side, q on the other, we can return our current root. If both sides contain p and q, or one of the sides contain p and q, then we recurse on that side, because we know that there is potentially a lower common ancestor. If one of the nodes happens to be the root, then we just need to find the other one to make sure that it exists in one of the containers. And that's pretty much it. I think this should be correct. Maybe there's some compilation errors that I missed. We'll see. Let's run a quick run code result. So it looks like if root.left looks like Kotlin is not very supportive of truthy statements that don't explicitly say what they do. And we will also want to add our value of our root, not just our root itself, because it expects a node. Okay, so it seems like it worked for this statement. Let's run it through the other statement, or the other two examples. Looks like they worked. Let's toss in a submit and let's see where we end up. Okay, so it looks like we ran into a TLE. And oh boy, this is a large test case. So it seems like our solution is not fast enough. Well, why isn't it fast enough? I think the biggest part that's probably taking up a lot of room in this case is the fact that we are rebuilding our sets. So, repeated work. We are rebuilding our sets for each iteration down our tree. I guess the main thing is that within our tree, if we recurse on one side, then there will only really be one node which is removed, which is the root. So how can instead we how could we instead sort of manipulate our set in order to work a little bit better? Well, let's see. If we turn this in-order traversal into a post-order traversal, and let's run back our initial test case, just so it's a little bit easier. And rather than having a mutable set, we'll create a mutable list. We can keep the, or we can swap this out. So, actually, let's not. So why not turn our list or our set into a list? Well, I think the set actually provides a few benefits. The first is that dot contains should be constant time versus linear, because we can't get better with an unsorted list than linear selection. And we could always remove should also be doable in constant time. So we don't necessarily need the order to be a certain way. So what we could do instead is to create a new function, lowest common ancestor, with all the same function signatures. Along with a left set and a right set. And these will be nullable types. And what we could do is that we'll start off by building these sets. Actually, we could probably move most of this logic within. Let's think. Yeah. We can move the logic into here. And we can say return lowest common ancestor root pq null null. So we can say our left set, we'll call this left, and we'll call this right. And if our left side is null, or our right set is null, then we will create a new set and we'll build that set up. So of course, if both of the elements exist within one side, so 5 and 4, for example, here, right? Well, we have a left set and we have a right set. However, we know that the right set really isn't useful since we're recursing on the left. So we'll have to discard one of the sides regardless. However, we do want to keep the left set because it's full of good information about what is actually on the left and right sets. The main question I have now is how can we determine what is on the left side versus the right side subtree versus the right subtree of an array, or of the set, right? So the idea that I'm thinking about is that maybe there's a way to calculate the left and right subtrees from here. So basically we ran through this initial iteration through our left subtree. So we have the whole thing, but now we need to remove elements from it. We need to remove elements from it in order to figure out sort of which items are on the left and which items are on the right. And then we can sort of build up a left and right subset without actually having to reiterate over the array, or the tree. And the problem is that the set is unordered, right? The set is unordered, so we can't really necessarily have something like that. Still thinking about that list because of the ordering. But I wonder if it's necessary. Let's see. So let's say, suppose that that P and Q exist on the left subtree. What information can we get from our current set? I have a feeling that we might need to convert this set back to using tree nodes rather than integers, but we'll get back to that in a little bit. We can remove the item with the value that matches the subtree. So for example, we can remove 5 from our left subtree because we know that, well, because it's our root and we don't want it to be really part of any subtree. Alternatively, we could have it as part of both subtrees, and then we can get rid of the argument for the 2 edge cases up here entirely. Could do that. But I think the current way that we have it, where we call to build up the set on the left and right subtrees, is perfectly fine. But what else should we remove, or could we remove, from these subtrees or these subsets in order from these sets in order to build up the subset? That's a good question. Well, if we know the node, we know at least the items on its left and right. So if we knew 5 as a node, we know about 6 and 2. We know that 6 and 2 are the left and right pointers, but we don't necessarily know, I guess, that 6 and 2 are like what their subtrees contain, right? So that's another issue that we can that we're running into. I'm just thinking again whether or not that list will actually be of any use. Because if we run it in a particular order, we should know sort of which items belong to which subtree. And that might not actually be a bad idea. However, that would make contains, rather than being a constant time solution, it would be a linear time solution, right? Because contains, we would just have to sort, or we'd have to check through potentially the entire array. What could we do? I mean, there is a trade-off there, right? We would know the indices, or we would know sort of we would know we would know where we needed to be with regards to we would know where the indices are, would we? Probably not, actually. We would know that the 5 here has a left and right, but we wouldn't actually know where those indices are. So that might not necessarily be so helpful. Let me think about this some more, and then I'll get back to you. Honestly, I'm out of ideas as to how to make this faster. The one thing that I did try is that I started to pass in this left and right subsets. The idea is that we can keep this subset here. We just removed the root. Well, in my case, I didn't even remove the root. But the idea is that we can take this tree, this subset, we can keep it for the next iteration. We only need to iterate for one of the sides. And it doesn't really matter which side we iterate on. I think in my case I favored the left or the right. Doesn't really matter in this case because it's the set that encompasses the entire subset. But then I also took another subset, another second layer subset of this left or right subtree, and then I just got the set by subtracting it from the other one. So I essentially halved the number of sort of set rebuilding, but it's still not good enough. So I feel like there's probably a solution here where you can use the same set that you've obtained from the previous iteration, and you just don't need to rebuild the set at all after your first iteration on the left and right subtrees. But I'm not sure what that solution looks like. And in the interest of time, this is where I throw in the towel once again and take a look at the solution to see what they actually did. So let's take a look at the solution. First, are to be searched in a binary tree, and then the lowest common ancestor are to be found. Once we reach the desired nodes P and Q, we can backtrack and find the lowest common ancestor. So rather than doing a top-down approach, they do a bottom-up approach. Okay. Let's grab all of this stuff and put this into, call this the failed attempt. I can grab the rest of this here. Okay. So the idea is that rather than going top down, searching within all or the entire subset or set of nodes, go bottom up, search for the nodes and compare ancestors. Let's see if we can do that. Let's see if we can do that. So we need to construct the list of ancestors for a root and our target. And this will return a list of, we can say integers in this case. We can say a list of integers because, well, it's we're fine to deal with. We can deal with the list, we can deal with the set. Doesn't really matter in this case. Actually, we'll go with the set. I think a set actually makes more sense. The problem then becomes, how do we know, how do we find P and Q, right? Well, we could do a traversal, but we don't actually really know which way it goes down. It might be better to actually keep this as a reference. Maybe. I have maybe an idea. Well, if our root is null, we just return null. If our root left is not null, then we can go down that route. If our right side is not null, we can also go down that route. Now, what do we actually want? So let's say that we go down this route. We go all the way to the left. And let's say that we find 5 here. So if root is root.val is equal to target.val, remember that each node's value is unique in this case, then we can return our root. So this will return a tree node up. Let's see about something a little bit more different. like this 4 in this example 2. So if we go 3, 6, or we'll go down to the 6 first. Then we'll go to the right. Then we'll go to this. We'll go to the right. Then we'll go down. So the 7. And then we'll go to this 4. So what we can do is we'll have this node set here, or we'll call this ancestor set, which is a mutable set of integers. This will return actually a tree node question mark. We'll say val left is equal to ancestor set root left target. If left is not null, then we can the idea is that once we find our value, we want to return, or rather, if we found our value, we want to start returning. So let me think about this a little bit more. So let's say that we go left, nothing's there. We return null. We go right, we go left, return null. We go right. We found this. So this returns our root. So if ancestor set root.right target, if our right is not null, then we return our root. And same thing here. Because if we have found a root, or our target, then we can return every value up from there. If we have not found it, then it doesn't matter. We can say root p, and we can create a new mutable set, or we can say val p set is equal to mutable set of int. We can print this ancestor set, or we can do this ancestor set thing. Not print it out, but then we can print out the set. Here. And then we can just return root here just for testing. So the idea is that we create a set, and this should return the list of ancestors. But we need to actually add those ancestors as well. So ancestor set dot add root. Ancestor set dot add root. Find ancestors. I think that's a more descriptive name of like what we're actually doing. And then here as well, ancestor set at root. And then we return it. And if nothing else, then we return null. Let's go ahead and take one of these example cases from the beginning. And let's see this play out first. Let's pass in this ancestor set by reference. Oops, looks like I misspelled it. Oh, and we want the values. Is that all? Target.val. This target. If root is null, return null. If p is null or q is null, return null. And let's make this target a non-nullable tree node. And let's hope the compiler is smart enough for that. Cool. So here in our set, we get 5 and 3. And let's actually take a more meaningful example here, which is example 2. And for our first root for p, we should get, we actually want to run this on q, actually. Yeah, we're going to need to do both of these, so let's just do q set. And print line q set. So this q set should return 4, 2, 5, 3 in any order. 4, 2, 5, 3 in any order. Cool. Right. So that gets us the actual ancestors of these nodes. Of course, in this case, we really have to do 2 full traversals. So O of n for both of these. But now we can say q set for each ancestor. Is this set in order? Because now the next question is, how do we know which ancestor is the lowest? Well, assuming that the set is in order, however, I'm not sure if the set actually is in order. Because, like, is it in the order in which that we insert them in? If that is the case, then we can actually go through and do this. Otherwise, we would probably have to transition into using a mutable list instead. Which I guess isn't the end of the world, but still is expensive, right? So for each item in the Q set, or actually, how do we know? Again, the question remains of how do we know which value is lower? Assuming that the set is in order of insertion, it should come up first. But how do we know if it came up first? And I don't think the set actually has... Oop, did not mean to do that. Let's take a look at the set. Preserves the order of elements insertion. Okay. Is there a for each indexed? There is. Well, we can say if pset contains ancestor, we can say var lowest ancestor starts off at the root.val. Or var lowest ancestor index. Is there an index of? Is this a linear search though? I'm not sure if I would want to use this. Because it's just iterable, right? Yeah, so that probably is a linear scan. How do we tell? Well, we'll say integer.max value. We'll start this off. If it contains this ancestor that we have here, and our index is lower than our lowest ancestor index, then our lowest ancestor index will be equal to our index, and our lowest ancestor will be equal to ancestor. And we'll pretty much do the same thing for the pset. So if it is contained in the qset, and it is lower, then we reset the lowest index and the lowest ancestor. So 4 doesn't exist in this set, 2 doesn't exist in this set, 5 does exist in this set. I wonder if it's possible to make an argument here that the first ancestor that you encounter in either of the sets is the lowest counter, or is the lowest ancestor. And I think that's pretty much what I do, right? I just check the set to check which one is lowest in this sort of way. But I do wonder if it does actually work the way that I expect it to. If one side is incredibly unbalanced, maybe then we want to check the longer of the sets. Or do we want to check the shorter of the sets? Let's check the shorter of the sets. Because if an answer is guaranteed to exist, that there must be an ancestor between them, then it should come up first in the shorter set, I think, no matter what. So we can sort of get rid of this logic, and we can say var shorter set is equal to pset.size is less than, or if pset.size is less than qset.size, then we select pset, else qset. Then shorter set.for each Then we need to do an other set because we don't know which one that is. If shorter set is equal to p set, then q set, else p set. If other set contains, this would be ancestor, then return ancestor, no. So basically we're relying on the fact that the solution should exist within the shorter set, and if it is an ancestor in the shorter set, then it should come up first, because we start returning in the insertion order from the lowest item, right? So it should exist before. And then the other idea is that if one of them is an ancestor of the other, for example 1, 2, well, one set will be, the set that exists at the root level will be 1, and the set that exists at the lower level at one of the children should be 2 and then 1 for this example 3. And in this case we will check out 1, and 1 exists in the longer set, and that seems to work. So I think maybe this will work by checking the shorter set. We'll see. Contains ancestor. Because we want to return the node itself. So let's actually turn this into a tree node. Okay. So those add those. And this is fine. This actually still remains the same. This should be a tree node. Let's see, because we need to return the node itself, not the... Okay. Works for the first case. Let's run the other cases, the other example cases. Okay, let's try to run this monster case. Let's see where we end up. Okay, let's run a submission. Let's see where we end up. Okay, it's still pretty slow, but it actually goes through, right? And I'm sure that if I actually hammer the submit button, because for some reason LeetCode just does this. I don't know, maybe the solution is just slow and it won't be any faster, but for some reason sometimes you just run it again and LeetCode just makes it go faster. I'm guessing there might be some like cold start stuff, assuming that LeetCode is using some weird serverless thing for the submissions maybe. But in any case, yeah, so this seems like a pretty standard solution, followed like pretty much the first paragraph of the solution. Unfortunately, we couldn't figure this out in the first place. I think maybe if I thought about taking a different approach, I might have thought about this, but sometimes you just get pigeonholed down one area. And this is just better because you just have less items to look at, right? You don't need to build up a subset of like a few thousand nodes or whatever every single time, so it's just better. But in any case, I hope you learned something, and I'll see you for the next problem.